All right, we are at 19.8, magnetic force between two parallel conductors. Let's get back, let's get right to the PowerPoint. And you're going to see, now we're going to look at the current in I2. Um, the current is going in this direction, and it creates a B field uh, wrapping around it using the right-hand rule. The I2, you can see it forms B2 that cuts right through right through the uh, current of I1. Well, so now we have a B field coming out of the page, current going this way, so the force is downward. The force is downward, so the field, the B2 field is mu zero I2 times 2 pi d, where d is the distance between them, and that's the radius, how far it is. You remember it's mu zero I over 2 pi r. Well, r in this case is the separation distance d. Um, and so force 1 is equal to B2, that B2 from the I2 times I1 times L. So that's mu zero I2 over 2 pi d I1 L. So the force is mu zero I1 I2 L over 2 pi d. So the force 1 um, divided by L, let's see, force 1 divided by L is um, mu zero I1 I2 over 2 pi d. Now, I'm not so concerned uh, about this formula as I am about you knowing what happens um, with the currents. And I've got a little Mathematica file. I did not write this. I forget who the author is on, let's see, the author is SM Blinder. Um, but you see here the I1 and I2 are both going in the same direction. And look at the force between them. The force is towards each other. See the blue lines here? Now let's change the radius as you can see what happens to the blue lines as I make them closer and closer together. The force gets bigger. You'd expect that because the magnetic field, as one wire approaches the other, the magnetic field is getting stronger. So the force is getting stronger. And you can see as I move it out, the force gets weaker and weaker. So let's put it somewhere here in the middle. Now, the current is 4.2. They're both going in the same direction. The force is inward. Now, let's take one of these. Let's take I2 and reverse its current. Now, let's try to make it the same, 4.2. Now, it's negative 4.2. Now, notice the force. The force is away. So if the currents are going in the same direction, the force is going to be towards each other. If the if the currents are going in the opposite direction, the wires are repelling each other basically. So they're repelling each other. Put it over here. They're attracting each other. The force is inward. Go back to the negative. The force is outward. So same direction, the force is attracting. Opposite direction, the force is repulsive. That's the main thing I want. That's kind of a quiz question, right? If two conducting wires have current going in the same direction, the force will be towards each other. That would be a typical question. Or I might ask if they're opposite direction, then they repel each other. Okay, let's go back to a new share and go back here. Now there's some things here. Definition. They use this as a definition of the ampere and the coulomb. The definition of an ampere: if two long parallel wires 1 meter apart carry the same current, and the magnetic force per unit length on each is 2 times 10 to the minus 7 Newton per meters, the current is defined to be 1 amp. Now, the definition of a Coulomb. If a conductor carries a steady current of 1 amp, the quantity of charge that flows through any cross-section is in 1 second is 1 Coulomb. Okay, and I think that's it. Yes, that's it for this little section.